Well, good morning. Now in this second session, we will continue our talk on logic synthesis, but something in the perspective of tool. Now, I hope you have an idea what a tool is. Perhaps you have worked with MATLAB and all those. Those are actually tools that make our work easy. When the design becomes very huge, we cannot handle manually the small bits and bits ourselves. At that point, the importance of tools comes in. Now, till date we know VLSI design flow. Now, when we are about to design a digital chip, we start from the specification, then we fix the architecture, then we fix the logic design, then go to circuit design and device design. What is specification? In specification, we formulate the problem, that is the problem we have to solve. Means the problem statement, formulation of the problem is done at the specification level. At the same time, the solution of the problem, it is decided which part will go to the hardware and which part will go to the software. And here we are only interested about the hardware portion. Okay. Now today we will talk about logic design at this level. We will talk about this level. We have gone through architecture in the ADIC class. We will talk about logic design. Now what happens at logic design? Now as I said, we will go for tools. Now what is tool? Tool is something computer aided logic design. With the help of computer, we design our architecture. Now the inputs for this design is your constraints and the cell library. We will talk about this in detail, what a constraint is and what cell library means. Now at this level, the computer aided logic design generates the optimized gate level netlist. Optimized means we have certain constraints. What constraints? We can have area, constraint of area. We can have constraint of time. Now the design is optimized to meet that constraints and generate something called a netlist. What is a netlist? We will see. Now if the output of this level, if meets the constraints, we will go for the circuit design. So we will only concentrate in this level. Now what is logic synthesis? In logic synthesis, we have from the architectural level the RTL model of the hardware. Hope you know what an RTL is. RTL is a synthesizable Verilog code. Okay. Now it is written in HDL and the output is optimized gate level representation. Now this is actually done by a logic synthesizer. The input of the logic synthesizer is the code and the output is the optimized netlist. Now what netlist is? Suppose we have a small design A, B, C, D. These are two AND gates and this is an OR gate. The AND gate, this instantiation of AND gate, we call it AND 1, B, and this AND 2, this OR 1. The output we will call O. Okay. Now for a AND gate there are two inputs, in 1 and in 2, and output we will call out. Okay, so what a netlist is, netlist will say who are there, means which gates are there and how they are connected. Like it will say A is connected to the in one port of AND 1, B is connected to into port of AND 1. Similarly, the out of AND 1 is connected to in 1 of OR gate. So what is this? This is the netlist. So we can, if given a netlist, we can identify what the our logic design is. So this is the netlist. So what a logic synthesizer do? There is a Verilog code and it will give an optimized netlist. The synthesis process has three parts. First is the translation, second is the logic optimization, and third is the gate mapping. We will talk a little bit about this, what these things are. In this figure, suppose you can see here there is a Verilog code. If A is equals to 1, when A is 1, the Y should be C and D. Else, if B is 1, Y should be C or D. Else, Y is equals to C. Now, when we draw the logic design on hand, that is the simplest. You can see there, if you decode this, this will give this Verilog code. So this is the simplest translation process. Now this is done by the logic synthesizer. Logic synthesizer then optimizes the design. Why? To meet the constraints. Obviously there will be some constraints. If there are no constraints, it will not optimize it. Okay. Next, we will talk what actually happens in a tool. We will talk about translation and optimization. So we saw that the input is a Verilog or a VHDL code. At the first level, we translate it. When we translate it, what we get? Unoptimized netlist. Then this unoptimized netlist, and on this unoptimized netlist, we perform area and timing analysis and get something like this. What is this? This is the plotting of timing and area. So we get that for this netlist, we have a speed, the time taken for input and the time between input and output is this much, and the area it will take on the chip is this much. Okay, this is the area time analysis of the unoptimized netlist. Now this unoptimized netlist, we apply three types of constraints. What are constraints? We will talk a little bit. Now these constraints will govern the optimization process. Why? The main goal of optimize is to satisfy these constraints. So here we will perform three different optimization process as per the constraints. Again, for the 3 optimized netlist, we perform the area and timing analysis. What we get? We get 3 points. What for this, the time taken is this and the area is this. Now, so this is our output, and after optimization we get the netlist, that is the optimized netlist, that is the requirement of the logic synthesizer. Now, talking about constraints. What are constraints? Constraints specify the design goals that are to be met. Now, the constraints are of two types. One is global and another is circuit specific. Global means what? Global constraints are applicable to all designs. What are these? These are library process factors. Now we use a library, means we will talk about library a little bit later. Now there is something called process factor. Then the operating voltage, it is fixed, that we will provide 5 volt. Your design should work under 5 volt. If presently it is requiring 8 to 10 volts, you have to optimize the design such that you would require 5 volt. Okay, so these are the constraints. Operating temperature. Okay, these are what? These are global constraints, that these constraints are applicable for all designs. There is another class of constraints, that is the circuit specific constraint. Circuit specific constraints are area, timing. Timing is input output loading, input fan out. What is input fan out? Means suppose there is a AND gate. Now if this AND gate drives 3 other gates, then we call that this has a fan out of 3. Now timing depends hugely on fan out because of those capacitance delay and all those things. Input arrival time, and obviously the minimum clock frequency. Another constraint is power. Now different constraints gives different optimized circuits, but all these circuits have the same functionality. Now we talked about library in our here. In the computer aided logic design, their input is the design constraints and the standard cell library. Now what a library is? Now library is contains a set of gates. For example, suppose we have a library in which there is an inverter, 2 input NAND, 3 input NAND, 2 input NOR, and like this. What does this mean? That whatever be our design, we have to implement it using these gates. These are the basic gates. Means we have to implement our design using these gates only. So this is what a technology library contains. Now with these elements, there are some attributes attached. What are the attributes? That is the technology on which these are being developed, whether it is based on CMOS or NMOS. Then the input capacitance of these gates, the maximum fan out of the gates, the rise and fall time. What is rise and fall time? Means since their capacitance is involved here, at the input, if we apply a pulse like this, a transition from 1 to 0, this will actually in practical will appear as a this. So this is the fall time. Similarly, any transition from 0 to 1 will appear like this. This is the rise time. Similarly, the process 0.65 micrometer. What does process means? Means whenever we are going to build so process is actually in the CMOS, the channel this is the process is governed by this channel length. So when we say that we are building our design on a 0.65 micrometer process, means the channel length is 0.65 micrometer. Similarly, now we this is the present design. Present designs are going at 0.65 micrometer. Similarly, the technology library has attribute temperature, means the operating temperature. It will fail above this temperature. This is all involved in the technology library. Now, synthesis process is divided in 3 steps. The first is the pre-synthesis process, then the actual synthesis, and then post-synthesis process. What happens in a pre-synthesis process? At first, when a logic synthesizer gets a Verilog code, it analyzes it. Means what are there? Is the Verilog code actually synthesizable? All those things are decided at this level. Then it does partitioning of the design. Now, what is partitioning? Partitioning is nothing but a division of a complex design into smaller parts. Now, suppose we have a design which contains some registers and some gates. Now, what partitioning does is divide it into smaller blocks. The main idea behind this is to divide and conquer. Now, why partitioning is done? Partitioning is done for better synthesis results and reduction in the compile time. Then in partitioning separate distinct functions, the distinct functions are separated or the similar functions are merged, and the reuse of existing modules. The modules which are actually present now, we will use it in the later design and create modules for future use. Now, again coming back to the process translation. Now, what happens in translation? Suppose in design we have an statement if then else if, like this. Always at select or A or B or C or D transitions do this. What? If select 2 means select is a 3 where. If select 2 is 1, then output is assigned A. If select 1 is 1, then output is assigned B. If select 0 is 1, then assign C to output, and in other cases assign D. Now here, now when select 2 is 1, A is assigned to the output. When select 1 is 1, then B is, if select, now when the control comes here, when this is not fulfilled, this means what? Select 2 is 0. Select 2 is 0 means this is valid. So when select 1 is 1, then B is available at output. Fine. Now if this statement is also not valid, means select 1 is 0, select 2 is also 0, and if in that case if select 0 is 1, if select 0 is 1, then select, now this is valid, this is valid, so C is available at the output. I hope it is clear. And else means if all of these are 0, then D is available at the output. Now this is what happens in translation. Now I am taking another example, the for loop synthesis. Suppose whenever there is a change in value of A or B, do this. What? For I is equals to 1 to 6, assign to example I, means I0, I1, example I, assign AI and B5 minus I. Now what it does is, now here this loop runs for 6 times. So it will instantiate and 6 times. Okay, and to every and, now for here when I is equals to 0, A0 and B5. Clear? When I is 0, assign A0 and B5 ANDed, and it is assigned to example 0, example I is 0. Fine. Similarly, when I is equals to 1, then and A1 and B4, A1 and B4, assign it to example 0. Clear? Now after translation, the logic synthesizer goes for optimization. Why optimization is actually needed? Because there are certain design goals that has to be met. That is, what are these design goals? The design goals that are there are minimal, are to meet some area constraints, to meet some speed constraints, or some environmental conditions. We use here minimal and maximal, not minimum and maximum. Why? Because the area, suppose we have a design, it has an area A1 and speed x1. We cannot say that this is minimum, because actual area, minimum area that can be, the actual area that can be attained is this. Okay, but we are somewhere here. So what we, at this point, the constraints govern our area, the constraints govern our speed. Now this area and speed are minimum for this particular constraint. They are, and that is why we use the term minimal, not minimum. Fine. Now design space exploration. There is a term design space exploration. What is that? That is analyzing the design for optimization. Where we can use, where we can optimize the design. It will search for the possibility of optimization. Now there are 3 levels of optimization. Optimization can be done at the architectural level, can be done at the logic level, or could be done at the gate level. Now we will talk a little bit about optimization here. It will be taken in details in some class later. Not architectural design, architectural level optimization. Now a type of optimization that is done at this architecture level is your resource sharing. Now it is obvious, when we share a resource in any design, the amount of resource that we actually require will decrease. Now suppose we have something like this: if select, then assign to sum a plus b, else assign to sum c plus d. Now what we will design is something like this: a plus b, c plus d, and a mux here. If this is 1, this is 0, this is select. When select is 1, a plus b is the sum, and when select is 0, then c plus d is the sum. But what the logic synthesizer do? It will now what it will do? Now here look, the functionality remains same. When select is 1, a is available here. When select is 1, b is available here, and the output is a plus b. When select is 0, c is available here, and here d is available here, and the output is c plus d. Now here we are using 2 adders and 1 multiplexer. Here we are using 2 multiplexers. Now we know that the area for a mux is much more less than a adder. So we have the resource is shared here. Means there are 2 ANDs, but we are using here a single AND to perform 2 additions under different conditions. Similarly, we can go for operator reordering. Now suppose we have a function a plus b plus c plus d. What can be one possible? We add a, b, then add c, sorry, then add d. So if we go for speed, then there are 3 adder delays for the output to appear. Now if we design it like this, if we do it like this, the functionality remains same, but the delay is now 2 adder delay. Fine. Now before optimization, the logic synthesizer does a particular things that is called resolving multiple instances. Now what is this? Suppose in your design you have a module A, you have another module B. In this module B, you instantiate module A twice. Say twice. If module A, call it something like, just call module A twice. Now what has happened, suppose in any design you have called like this and AB and say O1 A1 B1 O2 A2 B2. Now if any code, if these two statements appear, then what the logic synthesizer do? It will generate two AND gates with output like this. Similarly, when a logic synthesizer first compiles module A, then when it goes to module B, it looks that there are two instances of the module A. Now what here comes the problem of module multiple instantiation, and the compilation is aborted. Why? Because it cannot do something like this. So the synthesizer, there is an provision for resolving this multiple instantiation. Whenever it sees two calls for the module A, it compiles module A twice and generates two modules, say A1 underscore A underscore U1 and A underscore U2, and uses A underscore U1 at this point and A underscore U2 at this point. Clear? Yeah. 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 Problem was because yeah, you said that these two instance names are given, and whenever these two instance names are given, it generates two uh, two uh, modules, A underscore U1 and A underscore U2, means just copy of the module A twice. Okay, suppose as it was given that and say and A1 and A2, what it makes? It makes an and A1 and A2. The same thing happens here. Yeah, but the module A is compiled first. No, it is compiled only once. Means what? It has make only one copy of the module A. Two compilations are needed.
The problem is with the unify. See, you have designed say one module, say big module, okay, sufficiently big, and you have called it twice. Now you can say that you can guide the tool of the logic synthesizer that you compile it once, compile in the sense optimize it once, and use the same thing and hook up in your bigger module. Or you can say that you can instruct the tool depending on your situation and your choice that you unify both. Say it's called A1 and A2, and if there is a provision of optimization, to optimize them in different ways, because optimization depends on the input load and your timing budget, and it may be in the situation wise those budgets might be different. So here this unifying means you optimize them in treating them separately and then hook up. That's the
Okay, fine. Next, at the optimization at the logic level. At the logic level, there are two processes run one after another. One is flattening and another is structuring. What happens in flattening? In flattening, your design is replaced by a sum of product form. Means what? The entire combinatorial circuit is converted into something like this, sum of product terms. Okay, that this is only two levels. Your all combinatorial circuits. Obviously, there are some exceptions to it. Some types of combinatorial circuits are not flattenable. Now, at structuring is just it is two level. Now, after flattening, we do the reverse process. That is, we convert the flattened design. We actually factor it, factor the design into multiple level. Now we will look for an example. Suppose we have a design suppose it is synthesized. We synthesize it then using two input gates only. What will happen? First, A and B are ANDed, then the output is ANDed with C. Then Y1 is given as MD. Okay, Y1 is L plus AB. Now AB is available as M, so Y1 is equals to L plus MD. Y2 is equals to M plus C plus D. This is actually also done as first M plus C, then this plus D. So what is the structure? Structure is AB, the output is ANDed with C. This is your L, then L, then this is your M, it is ANDed with D, and this L, and this is ORed. Okay, this M is ORed with C, and then again ORed with D. Now if we flatten this structure, in flattening what is done? Sum of product. So Y1 is written as ABC plus ABD, sum of product, and Y2 is kept as AB plus C plus D. This is actually what flattening is flattening. Then we structure it, that is we factor it into multiple level. What we do? We factor, first we perform this AB, then we perform CD. Now here comes the intelligence of the logic synthesizer. Then it performs Y1 as Mn, Y2 is M plus N. Clear? M is AB and we can write this as AB into C plus D, right? Taking AB out. Now what is AB? AB is M, and what is C plus D? C plus D is M, and here it is clear. So if we synthesize this, what we have? We have an AND gate with inputs AB and OR gate with inputs C and D. Then again we have an AND gate, and here we have an OR gate. So look, earlier we were requiring 1, 2, 3, 4, 5, 6 gates. Here we are requiring 4 gates. Okay. So this is logic level optimization using flattening and structuring. Now we have seen that we have covered translation, we have covered logic optimization. Now gate mapping. Now what is gate mapping? You have an technology, that is gate mapping is actually technology mapping, also called library binding. What happens in technology mapping, that the Boolean network in your design is rewritten in terms of the available functions. Available functions means the gates in the library. Is it clear? That we talk that in library we have a set of gates. In technology mapping what happens, that the Boolean network is mapped, is redesigned using these gates only. Now what technology mapping, in technology mapping optimization problem also comes. There is something called a cost function. Okay, the aim is to minimize the cost function. So there are multiple cells available in the library. You have to replace your design using these cells only. So what technology mapping is actually a pattern matching problem. What? That you have to find a pattern that minimizes the cost function, that is basically an area delay cost, that minimizes this area delay cost. Now the most popular approach is the DAG covering, that is directed acyclic graph. Just we will explain DAG using a problem. Suppose we have a design like this: NAND, NAND, inverter, NAND, inverter, NAND, inverter, NAND, like this. Now you have to replace this design using a library is at your disposal. Just you have to replace this design using this only, such that your cost is minimum. Now some costs are obviously attached to this. Now the process here is like this. The netlist is converted into normal form. The available netlist, the netlist available for the to the technology mapper is converted into normal form. What is normal form? It is converted into a design which only contains 2 input NAND and inverters, nothing else. We know that NAND is an universal gate, means all AND or XOR all can be replaced by NAND. So in normal form, we replace this netlist using 2-input NAND and inverter. Similarly, the gates available in the library are also converted into normal form. This, in theory, we call the normal form of the netlist we call the subject DAG, and the normal form of the library gates we call it the primitive DAG. So our goal is to minimize the cost covering of the subject DAG, that is the netlist at our disposal, using the primitive gate. Now, suppose in the library the information is given that you have an inverter which takes an area of 2 units. You have a NAND, 2-input NAND, which takes an area of 3 units, so on and so forth. Now, in the algorithm, it is said that the library gates are converted into normal form. Here we convert the gates into normal form. Inverter is inverter, NAND is NAND, 3-input NAND is converted in normal form like this. Okay, NAND inverted means this is actually ANDing, then again ANDing, and then inverted. Similarly, NAND 4 means 4-input NAND is converted to normal form, that is NAND and inverter like this. NAND, inverter, NAND, inverter, NAND. Now, the library has an AND OR inverter with 2 inputs to the AND and 1 input to the OR like this. This is an AND, 2 inputs to the AND, there is an OR, 1 input to the OR and another inverter at the output. Okay, cost area is 4. It is mapped in the normal form like this. Similarly, we have an AND OR invert with a cost area of 5. Now, suppose the we will go for area covering. Now we keep in the circuit, we see that there are only NAND and invert. Okay, so to convert it into normal form, we do not require to substitute any gate. Okay, now one of the possible covers is like this. We take all the gates individual. Okay, now we see that the cost of a NAND 2 is 3. Okay, so all NAND 2 are given an cost of 3, and we see that inverter has a cost of 2. In the design, we see that there are 7 NAND gates, 5 inverters. So the total cost area is 31. Okay, now we go for optimization. We try to go for another type of gate area covering. Suppose we take this NAND, this inverter, here we take this. Now, oh sorry. What? Now here we see that this is actually 3 input. So this is actually nothing but your NAND 3. NAND this is actually AND OR invert. This is actually AND OR invert. So this has an area 4. This is 3 input NAND with an area 4. Similarly, this is also a 3 input NAND with area 4. So here in this case, the total area cost is 17. So obviously we will replace our design using these types of gates from the library, so that we have a minimum cost in terms of area. Okay, that's all for logic synthesis. Any questions? Thank you.